All right, AP Psychology. So we are going to start our next unit, which is the biological basis of psychology. And so we're going to be looking at our neurons, neurotransmitters, and how that impacts some of our mental health and emotional health, as well as the different parts of the brain and how all of those contribute together to affect the way that we behave and interact in our emotions. So there's a lot to learn and we need to get started. And so really, before we start labeling this neuron, a neuron, for the most part, is really just a nerve. And in this nerve, what it does for us is it sends a message to the brain, and it decides, are we going to listen to this message or not? And so that's kind of the process here. So let's go ahead and start labeling away on our neuron. So the first thing that you're going to label is what we call the dendrites. And the dendrites, if you put your hand up here, and don't worry, we're going to be learning all kinds of silly things in this unit to help you remember the parts of the brain. But the dendrites, okay, those are those little digits, those little tiny little extensions at the end, and those dendrites, they catch those incoming messages, okay? The dendrites catch those messages. And then, once the dendrites receive that message is going to go to the soma. And the soma is kind of like, the heart. And there's a phrase, don't think with your heart. Well, the heart of this nerve is the soma. And inside that soma is the nucleus. And the nucleus is the part of the neuron that's going to make the decision of whether or not that message gets sent. So there's the nucleus, and when we talk about sending that message, this is an electrical process. And so when we talk about sending the message, we're going to use the word fire. And so the nucleus is going to decide whether it should fire that message through or not fire the message through. And then you've got the dendrites, the soma in the middle, and then you're going to stretch out your other arm here. And that is your axon, okay? And the axon is the longest part of the neuron. This is where that electrical message is going to travel through. That's the long extension of the neuron. And then within the axon, you've got a number of other little parts that are actually pretty important. The first is what we call the myelin sheath, And it's kind of this protective coating over the axon. And it's made up of fatty tissue. It insulates the axon, and that fatty tissue, it speeds up the transmission of the message. Without myelin sheath, that message could get kind of stuck up. Myelin sounds a little bit like margarine. Margarine is like butter. Butter helps things get really smooth. So myelin sheath. And then in between those little nodules, they actually look a little bit like sausages. The little space between the myelin sheath, those are called the nodes of Ranvier. And Ranvier is a person, he's the one who discovered that, and so he gets to have a part of a neuron named after him. So the nodes of Ranvier are the space between the myelin sheath. And then you can see on the picture there's a little dot on each of those nodules. And those are called Schwann cells. And they are actually non-neuronal cells. Okay, there's really no nucleus there. But the responsibility of the Schwann cells is that's what helps produce the myelin sheath. And again, the myelin sheath is what's going to help speed that message along through the axon. And then at the end of the neuron, those little, so you've got the dendrites here, the soma, and then the axon, and then at the end of the axon, little jazz fingers. It's like your fingertips, okay? Those are what we call the terminal buds or the terminal buttons. the axon terminal buds, axon terminal buttons, and those are the end point of the neuron. And that's where the neurotransmitters are released into the synapse, which we'll talk about here in a few more slides. And that's where that message gets released. And let's see where it goes, and let's see what happens and how it gets picked up, all of that. So those are the basic parts of the neuron. And again, those of you that are maybe a little more science focused, this is very basic. And again, this is a psychology class, not a biology class. So now we need to focus on the firing process, because that's how that message gets sent. And so we're going to look at it a couple of times. You're going to hear me explain this a couple of times, because for some of you, myself included, if you are not a science person, this might seem a bit confusing. But I'm here to promise you that if I can understand this, so can you. So let's go through the firing process. So what we are looking at here is an image. This is the axon. Okay, remember the axon is like that long arm. So let's just imagine that this is the axon, okay? And we're looking at it right here. And right now, this axon is in what we call resting potential. And when a neuron is in resting potential, it's not firing. There are no messages being sent. And you can look at this picture here, and you can see the axon here. And on the outside of the axon, you've got these positive signs here. These positive signs correlate to the sodium ions that stay outside of the axon. And then inside the axon is going to be potassium. And those have a mostly negative charge. So if you think about in resting potential, that arm of the axon, if you stretch it out, it looks just like a negative sign. And so during resting potential, there is a negative charge inside, and that's where the potassium ions are. So I'm going to throw one other little way to help you remember resting potential. And I'm going to use the words sweaty banana. And I just want you to write those in your notes, and when you come to class, we'll talk about sweaty bananas, and we'll see if maybe you can actually figure it out on your own without my help. Okay, so another word to describe what is happening here in the neuron during resting potential is to use the term polarized. And if things are polarized, they are on opposite ends. Think about the North and the South Pole. The North Pole and the South Pole. Those are polar opposites. And so in polarization, this is what describes the sodium ions on the outside and the potassium ions on the inside. Okay, they are away from each other. They are polarized. And to be honest, they kind of like it that way. They don't want to be near. They don't interact. They don't like each other. So during resting potential, let's keep everything nice and neat and calm. Let's keep the sodium on the outside and the potassium on the inside. And so when the neuron is in resting potential at this state, the term that's used to describe this is called homeostasis. And in homeostasis, it's like you're hanging out at home, okay? You want to stay at home. Why do you want to stay at home? Because it's your normal, happy, resting state. And this is what the neuron strives for, homeostasis. But that message has to get sent. It's like a little story here. The message has to get sent. And the neuron the nucleus released that message. And here it comes. And it's left the nucleus. And the nucleus has sent it to the beginning of the axon. And that impulse, that electrical impulse, or that message now is beginning to go through the axon. And so now things are going to get shaken up a bit, okay? And this is what we call action potential. We were in resting potential. Everything's cool, calm, homeostasis. But now here comes the message. It's time for action. And now things are going to happen. So when the nucleus decides to send that message, it's what we call an all or nothing principle. So if the nucleus says fire, here it comes. It's not like, oh, let me see. No, oh, I changed my mind. No, it's going to send the message. It's going to send it through the axon. Action potential is going to take place, and that message is going to be sent, and those neurotransmitters are going to get fired out through the little terminal buds. It's all or nothing. So that term intensity is really important. You have to remember that you don't just kind of send a message in a neuron. Okay, it has to have the strength and power the entire length of the axis. This may seem a little odd looking at a picture of a toilet here in your lecture video, but it's honestly a great analogy in understanding action potential. So given what you've learned so far about what happens when the nucleus sends that message, how do you think it could compare? How is it similar to the toilet in the firing process? So obviously you don't have a partner here with you, but maybe jot a few ideas down on your paper, and when we come back to class, we will circle back to the toilet analogy. So as I said, with action potential, things are now, they're just firing and things are happening. And what's happening is what we call depolarization. Okay, depolarization, because now those positive ions and negative ions, they are no longer going to be away from each other. It's not going to be that way anymore. And it's like a domino effect. And so what you see begin to happen are those sodium ions begin to rush in. And these little boxes here, these are actually gates, and they open up during action potential for those sodium ions to come in. And likewise, the potassium ions, they don't want to be in there with the sodium. Heck no, I'm going out. And so you have this depolarization that's happening as this message is being transmitted through the axon. And then the message has been sent. And off it's been sent, it's gone, it's on its way. And so now the neuron has to get back to that state of homeostasis. And so this point in action potential is what we call the refractory period. And this is the period of time after firing that the neuron is focused on resetting. And at this point in time, it's unable to fire again. So you can see that the sodium is shifting, moving back outside. Everything is going back to the place where everything feels good. I'm comfortable here. I can go back to that resting phase. Okay, so again, think for a minute. I'm going to bring up that toilet again. How is the refractory period similar to what happens when you flush the toilet? So just think about it, jot down a couple of ideas because we will talk about this. All right, so now we've got this blank diagram here, and I know it may seem excessive, but this can be a complex process, and we have left out so many details, but for what we need to know for psychology, you're going to be fine. So let's take a look at this and just let me clarify what you're looking at here. So you've got the neuron here, okay? You've got the dendrites, the nucleus, the axon, okay? And so right here in the axon, this arrow pointing down here, that's what all of this is. This little tubular box here, this is the axon, okay? So we've just magnified it. So action potential is about to occur. The nucleus has sent the stimulus, and now it has arrived at the axon. And so the sodium ions are on the outside, okay? The sodium ions are on the outside, and the potassium ions, the negative ions, the long straight arm, just like a negative sign, are on the inside. And so in action potential, when that message arrives, we are leaving the resting stage. We are leaving homeostasis. Those sodium channels open up, the sodium ions rush in. And then those potassium channels that were once closed, now they're going to open up. And as the sodium is coming in, the potassium is going out. And this is what we call depolarization. And then finally, the first sodium channels close further down the axon, because again, this is happening all the way down the axon. But channels further down open, causing the process to go the length of the axon until it gets to those terminal buds, and the neurotransmitter is released. So this is where we're at, okay? This is the neuron. You've got action potential that has taken place here, and that action potential is right here in the neuron, okay? And now this picture here is what those terminal buds actually are. And in those terminal buds, that's where all the neurotransmitters are going to hang out until, poof, they are released. And so these little tiny little circles here, these are all neurotransmitters. And at the end of action potential, the buds release those into this area right here. And this is what we call the synapse, okay? So those neurotransmitters, those are the chemicals, the chemical substances, and they cross the synapse. And the neurotransmitters are carrying the message to the next neuron, because another neuron with its dendrites, they're going to pick up on that message. So the synapse is really just a space. Synapse is the space between two neurons, okay? So they get released here, they're hanging out there, and they should get picked up by the receiving neuron. They may not pick up all of them, but they will pick up most of them. And so on the end of the dendrites, you could even add this to your diagram, on the end of the dendrites that are receiving that message, there are little tiny receptor sites, okay? And those are the points of the dendrite that receives the neurotransmitters. And they kind of are looking for their specific ones. Oh, it's kind of like being at the airport. I've got a little sign. Oh, serotonin, here you go. Here you go, here's your receptor site. Oh, endorphins, here you go. This is where you need to go. Okay, receptor sites receive specific types of neurotransmitters. So again, the synapse is simply just a gap. It doesn't have a role, it doesn't have a job in the firing process. So now we need to spend a little bit of time going through some of these neurotransmitters. And this is just kind of a bare bones introduction to these neurotransmitters. When we meet together again as a class, we'll talk about them more specifically and actually what happens if you have too many, you have an excess of a certain neurotransmitter, or if you have a deficit and you don't have enough neurotransmitters. I'm also going to be giving you a ton of mnemonics to help you remember these neurotransmitters, because again, there's a lot of them, but they are very important to know. So the first one is what we call acetylcholine. Acetylcholine. And acetylcholine's primary role is it's responsible for muscle contractions. So as I am moving my mouth, know that you can see in that little square, and raising my eyebrows and all of my muscle contractions, it's because acetylcholine is being released and allowing me to do that. Acetylcholine also has an important role in memory and learning, and one of the disorders that it's associated with not enough acetylcholine is Alzheimer's disease. Dopamine, primary roles there has something to do with movement. Dopamine will impact your thought process, but in bold there I have rewarding sensation, because that's above all the most important role of dopamine. It is your reward center, and if you feel good and you like what you're feeling, you are releasing all kinds of dopamine, and people like that feeling. If you don't, if you have too much, too little, dopamine is associated with Parkinson's disease, with schizophrenia, and it plays a huge role in drug addiction. And again, these are going to be things we go into a little more specifically during class. Serotonin is connected to your emotional states. It's also very much tied to sleep. A disorder that is hugely connected with serotonin is depression. And people who are suffering from clinical depression very often might be taking medication because they need to get their serotonin levels in balance. Norepinephrine, you may also be familiar with the term adrenaline, and we'll talk about the difference, and we'll talk about when it's norepinephrine and when it becomes adrenaline later in this unit. But for now, as a neurotransmitter, norepinephrine is responsible for physical arousal, for learning, and for memory. And it also is connected with depression and stress. And stress could be good stress, it could be bad stress. GABA is involved in inhibiting brain activity. And it's an important neurotransmitter because sometimes you need to stop or slow down certain things that are happening in your brain. And GABA recognizes that. And so sometimes it will interject, and the release of GABA will cause certain types of brain activity to slow down a bit, a very important function. GABA is also connected with anxiety. And then the last one are the endorphins. And endorphins play a critical role in our ability to recognize pain, and it's pain perception. Endorphins also make you feel really good, and there's something, the term having a runner's high. Very often if you've exercised for any amount of time, it could be, a massive workout, it could even just being walking outside, walking to your mailbox, and just getting some physical activity, your body, your brain will actually release those endorphins. But because of that connection with pain perception, endorphins also can result in issues with opiate addiction. So again, this is something that we will dive into deeper when we meet together in class. So the last piece of this lecture, we need to take a look at what we call agonists versus antagonists. And all of these are connected to neurotransmitters. And so if you consider something like drinking coffee, which is filled with caffeine, if we didn't have neurotransmitters, coffee wouldn't do a dang thing. You wouldn't feel the effects of the caffeine in the coffee. The reason that you do is because we do have neurotransmitters. So when there are outside substances interacting with neurotransmitters at the receptor sites on the dendrites, different things can happen. And sometimes they're good and sometimes they're not so good. And they both react different, or they both interact differently at the receptor sites. So I'm giving you here an analogy. And I want you to think of a house key. Okay, and the house key is what opens the door and lets you in, right? And then you have a master key, and that's kind of one that can be used whenever the house key's missing or you need an extra one. It's not the one you use all the time to unlock the house. And then you have another key, and it's just flat out the wrong key. It's a fake key. So we're going to use this key analogy here as we talk about agonists and antagonists. So when we think of an agonist, its role is to mimic neurotransmitter activity. We want an agonist to act just like a neurotransmitter. So it's kind of the master key, because we can take that key and fit it right in the receptor site, and it works just like the original, but it's not exactly the same. It'll do all the same things that neurotransmitter does. So an agonist mimics the neurotransmitter. And as we talk about agonists and antagonists, these are going to be things like medication and drugs, and anything that you put into your body that takes on another chemical role that could impede or interfere with the neurotransmitter. So an agonist, if something is labeled an agonist, it's going to act just like a neurotransmitter. An antagonist, anti, block. An antagonist is going to block the neurotransmitter activity. That would be the fake key. You're going to prevent that neurotransmitter from getting to the receptor sites and being picked up so it can go do what it needs to do. So an antagonist is going to block that neurotransmitter activity. And so as long as we understand the difference between an agonist and antagonist, when we get together in class, we can look a little bit more in depth and look at some additional examples of an agonist and an antagonist. Okay, so there is lots more to come in our biological basis of psychology. So I'll see you on the next one.